Now that we know that every polynomial splits completely in some splitting field, we want to see if we can detect any of the eventual structure of its linear factors uh, without having to go through and calculate all of them. In particular, we want to see if we can detect when a polynomial will have repeated roots. And it turns out that one of the most useful tools that we have for addressing this is something that has its start in calculus, the derivative. And we're going to define the derivative of a polynomial simply in terms of its um, coefficients and its exponents. We're not going to do anything involving a limit because we don't typically work in metric spaces. We don't assume that our fields have a metric on them typically. But we can still define the derivative of a polynomial. For a field f and a polynomial little f, which I'll give coefficients sum from I equals 0 to n of ai x to the I in the polynomial ring over f, we define the derivative of f to be f prime, which is the sum from I equals 1 to n of I times ai times x to the I minus 1. So this is just your standard derivative. So it'll be a1 plus 2a2 times x plus 3a3x squared plus etc. Up to n an times x to the n minus 1. Now, the reason why we care about the derivative is actually, it's not so much because of these numbers here. These numbers are what are important for calculus in terms of developing Taylor series and representations of functions, so forth. What we really care about is the way this derivative works as sort of an operation. And this derivative has the properties as follows. And the first three are very familiar. If we have f plus or minus g and take the derivative of it, that's the derivative of the sum or difference. If we have a constant times f and take the derivative, that's a constant times the derivative of the function. If we have a product and take the derivative, then we have the product rule applying. And this is the one, parts 1 and 2 are necessary in order for this operation to really behave nicely at all. The property 3 here, this is known as a Leibniz rule, is what's really going to give us useful structure. It's what makes the derivative a useful thing for us to have. And then finally, if phi from f to e is a field extension, then if I take the image of the derivative under the induced map, that's the same as if I take the image of the polynomial up to the ring E adjoin x and take the derivative there. None of these are terribly difficult to prove, especially any that are complicated can be done essentially by breaking it into pieces, making it using parts 1 and 2, making it just something that you have to deal with for powers of the variables. However, it turns out to be extremely useful. So we say that f has a repeated root A if f is equal to x minus a to the m, x minus a the m times g in some extension field, and if m is greater than or equal to 2. So a is a repeated root of f if the linear factor x minus a, which we know appears in the factorization of f in the splitting field, occurs more than once. So these repeated roots are what we're trying to detect, and Theorem 164 gives it to us. So let's let f, let capital F be a field, and little f be in polynomial ring over it. Now, there exists a field extension phi from f to e such that phi bar of f in E adjoin x has a repeated root if and only if the ideal generated by the function and its derivative is not equal to the polynomial ring f of x, or in other words, f and f prime have a common non-constant factor. So what we can do in order to detect whether a polynomial has a repeated root is simply to compare it to its derivative and see whether they have any factors in common in the polynomial ring over the field. So we don't even need to move up to the point where we're factoring them all into linears, which would defeat the purpose. We can just look and see whether the function and its derivative have a common factor in the original polynomial ring. Okay, so the first step of the proof is to show that f comma f prime, the ideal generated by f and f prime, is equal to the polynomial ring f of x if and only if phi bar of f and phi bar of f prime are equal to the polynomial ring over an extension field, and this is true for any extension field E. Now, this argument here is outlined in the notes. It's not particularly difficult. It's just noting that all of the operations in place, such as detecting whether or not your ideal is equal to the whole ring, is the unit ideal, and the derivatives here. I actually wrote the derivative in the wrong spot, but by the lemma, it doesn't matter where I write it. I can move it inside and outside, and it's basically just noting that all those things carry through from the original field to the extension field E. So we can work with this. So now let's suppose that phi going from f to e is a field extension, and phi bar of f in this polynomial ring as a repeated root. And we'll call it A, and it'll belong to E. So that means that phi bar of f is going to be equal to x minus a squared times g for some g in E adjoin x. So notice that that means that phi bar of f prime, the derivative, this follows all the same derivative rules that we're familiar with. So in particular, we've got that this is 2 times x minus a g plus x minus a squared g prime, just using the Leibniz rule and the definitions of the derivative. So in particular, this means that x minus a is a factor of phi bar of f prime. So this means that x minus a is a factor of both phi bar of f and phi bar of f prime. And so this means that the ideal generated by phi bar of f and phi bar of f prime is contained in the ideal generated by x minus a, which is not equal to the whole polynomial ring over E. So by the claim that we had at the beginning, that means that the ideal generated by f and f prime are not equal to the whole polynomial ring f adjoin x. All right, so that's one direction. So now let's suppose that f and f prime, the ideal generated by f and f prime does not equal all of f adjoin x. So in this case, this means that there exists g in f adjoin x with the degree of g at least 1, and where g is a factor of both f and f prime. So now let's let E containing f be an extension field containing a root of a. Containing a root a of g. So now in polynomial ring E adjoin x, we have that f is equal to x minus a times h for some h in E adjoin x. So therefore we have that f prime is equal to h plus x minus a times h prime. Just using the Leibniz rule, the product rule again. So now since g is a factor of f prime and so g is a factor of f prime and a is a root of g, we must have that f prime of a is equal to 0, because g of a is equal to 0 and f prime is a multiple of g. So that means that if we evaluate the equation involving f prime and h, this means that h of a equals 0. So this means that x minus a is a factor of h, and so that means that x minus a squared is a factor of f, because f is equal to x minus a times h, but then x minus a also has to be a factor of h itself, so x minus a squared has to be a factor of f, and so a is a repeated root of f. So polynomials, we can detect whether or not a polynomial will have a repeated root in some extension field by looking at the polynomial and their derivative and seeing whether the polynomial and its derivative have some common root. Now, when we're working with irreducible polynomials, we can be more precise. And in many cases that we consider, the polynomials that were irreducible polynomials are guaranteed not to have multiple roots. Now, for the following definition of following theorem, we need a definition. So we'll start with definition 165. A field F is said to be perfect if the characteristic of F equals 0, or the characteristic of F equals P and every element of F has a pth root. That is to say, for all x in F, there exists a y in F such that x is equal to y to the p. So being perfect means either your characteristic is 0, in which case you don't need to do anything else, or if your characteristic's not 0, then your characteristic has to be a prime number. That's true for any domain. In particular, it's true for fields. And so in order to be perfect and have a positive characteristic, p, then every element of your field has to have a pth root. As it turns out, every finite field is perfect, but one can construct non-perfect fields. They all, of course, have to have positive characteristic. And non-perfect fields don't have the nice property that we're about to prove. So theorem 166 says, if capital F is a perfect field and F is an irreducible polynomial, then F has no repeated roots in any extension field of F. All right, so let's see how this goes in the proof. So let's suppose that F is irreducible and has repeated roots. So we're basically going to prove the contrapositive here. We're going to suppose that we have an irreducible polynomial with repeated roots, and we're going to prove that the field F must not be perfect in this case. So by theorem 164, we have that F and F prime share a common factor of positive degree. Now, the only factor of positive degree of F is F itself, up to associates, because it's irreducible. So since F is irreducible, this common factor must be an associate of f itself. So that means that f is a factor of f and f prime. This means that f divides f prime. Now, if f prime is not equal to 0, we have a contradiction. Since in this case, the degree of f prime is less than or equal to the degree of f minus 1. So, that means that we can't have that the derivative of f is non-zero, because the derivative of f must always have lower degree if it's non-zero than the original function, or the original polynomial, I should say. So that means that we can conclude that f prime is indeed equal to 0. So this means that f prime is equal to 0. Now, if we were, as we're about to see, if we're working over a field of characteristic 0, this means that f would have had to be a constant, which doesn't work, because a constant can't be an irreducible. And so that's how we're going to rule out characteristic 0. However, the warning is that when we're working in positive characteristic, the derivative of a polynomial being 0 does not necessarily mean that the polynomial itself has degree 0. It doesn't mean that the polynomial itself is a constant. So let's see what's actually going on here. So let's let f be the sum I equals 0 to n of ai x to the I, which means that f prime is the sum I equals 0 to n of I ai x to the I minus 1. Sorry, sum from I equals 1 to n. So, since f prime is equal to 0, we must have that I times ai is equal to 0 for all I equaling 1 up to n. Now, an important point here, the ai's here are all coming from the field f, but the i's are actually integers, even natural numbers. So here when we say I times ai, we mean the normal thing we do when we have a number next to a field element. We mean that field element added up I times. So so keep that in mind as we go through this. All right, so now for any I with ai not equal to 0, we have that ai plus ai plus dot 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 plus ai equals 0, where we're adding these up I times. So that means that the characteristic of f must divide I. So for any I with ai not equal to 0, the characteristic of f must divide I. So this will only occur if the characteristic is a prime number p, which is positive, and where ai equals 0 when p does not divide I. So what we've got are, in our situation, we've assumed that f's irreducible and that it has a repeated root, which means that it shares a common factor with its derivative, which means its derivative has to be 0. When we work out what that means, it turns out this is only possible when the field has positive characteristic, and even in that case, the only powers of x which are allowed to have non-zero coefficients are the ones where the power is divisible by p. So we have that f, which was the sum from I equals 0 to n of ai x to the I, we can ignore all the indices which aren't multiples of p, because all ai is 0 if p doesn't divide I. So we can instead write this as the sum from j equals 0 to n divided by p of a pj x to the pj. All the other terms would be 0. Now, we've already shown that that the characteristic of f can't be 0. It has to be p. Let's show that f can't be perfect. So if f is perfect, then each apj is equal to bj to the p for some bj belonging to f. So that means that f would be equal to the sum from j equals 0 to n over p of, instead of apj, we write it as bj raised to the p x to the pj, which is equal to the sum from j equals 0 to n over p of bj x to the j to the pth power. And in characteristic p, powers of p distribute over sums. And so adding up a whole bunch of pth powers is the same as adding up the original, the bases, bj x to the j, and raising to the pth power. But this means that f is not irreducible, because we've expressed it as a product of other polynomials. In fact, as a power of other polynomials. So this is a contradiction. And so we must have that f is not perfect. So when working over a perfect field, in particular any field of characteristic 0, like Q, R, C, any irreducible polynomial has no repeated roots. An irreducible polynomial has a bunch of roots which are all distinct from one another when you go up to its splitting field. So then the question is, all right, well, can we say anything about the roots of an irreducible polynomial over an imperfect field? Yes, we can. We can say a little more. The roots of a polynomial over an imperfect field might be repeated, but all of its roots are repeated the same number of times. The multiplicity of each root is the same. So, Theorem 167. So let's let f be a field. F, little f inside polynomial ring over field f, an irreducible element, and E containing f, a splitting field for little f. All the roots of little f in E have the same multiplicity. Now here you'll notice I've assumed that our splitting field is actually a superset of the field that we started with. In general, we proved that splitting fields exist, that there's some field extension phi from f to e, but that field extension phi is going to be an isomorphism onto its image. And so we can essentially identify the field F with its image under phi, and so when we want a splitting field, we can, in situations like this, we can, for convenience, assume that that splitting field is actually a field that F sits inside, which makes the notation easier and doesn't actually lose us anything in terms of generality. So let's see how this goes. Let's let A and B in E be two roots of F. We know that there exists an isomorphism of F extension fields B going from F of A to F of B. And we know this by theorem, by a previous theorem which showed that each of these is isomorphic to F of Y mod little f. F adjoin Y mod the ideal generated by little f of Y. So they're isomorphic to each other. We've got this phi going from F of A to F of B. And furthermore, if we unwind all those isomorphisms from before, it sends A to B. Now, in F of A, we have that F is equal to x minus A to the M times G for some G in F of A adjoin X, and where M is the multiplicity of A in F. Now, we have that phi bar of F is equal to just F, because phi takes any elements of the base field F to themselves. So phi bar of F is F. And also, we have that phi bar of F is equal to x minus B to the M times phi bar of G. So that means that F equals x minus B to the M times phi bar of G. So that means that the multiplicity of B in F is at least M. So we took A and B and we showed that the multiplicity of B is at least the multiplicity of A. But this applies to any pair of A and B. In particular, it applies if we reverse the argument. So reversing the argument, we have that the multiplicity of A is at least the multiplicity of B. So that means that the multiplicity of A and the multiplicity of B are equal to one another. And that's true for any two roots of the polynomial f, and therefore all roots of f have the same multiplicity. Now, if the field f is perfect, then that multiplicity is just 1. But if f is imperfect, then that multiplicity might be higher. So let's see an example. So let's let f be the field z mod 3z adjoin y. Remember that this is the field of fractions. Of the domain z mod 3z adjoin y. So the elements of this field look like a polynomial in Y over a polynomial in Y, where the coefficients come from the field Z mod 3Z. So we can note that F is not perfect. The characteristic of F is equal to 3, but there does not exist an element Z in F with, there does not exist an element Z in F with Z cubed equaling Y, or Y over 1. And that's easy to see just by noting that if you take any polynomial or quotient of polynomials and cube it, then the resulting fraction will involve polynomials where all the powers are multiples of 3. In particular, you won't get anything with a power of 1. All right, so that means that we might have irreducible polynomials which don't which have repeated roots in some extension field. So in particular, now let's let F be x cubed minus y inside F adjoin x. I should write this as y over 1 perhaps. Now, in order to check and see whether this f has any repeated roots, it suffices to look at its derivative. So the derivative of f will be 3x squared minus 0, or the definition of the derivative just drops the constant term here. And 3x squared is equal to 0 because the characteristic of f is 3. So this means that the ideal generated by f and f prime is equal to the ideal generated by f, which is not all of f of polynomial ring. And so this means that f has a repeated root. But also, f is irreducible. Now, because f has degree 3, we can check this by noting that there aren't any elements of f which are roots of this polynomial. Now, be careful here because this isn't just a matter of checking elements of Z mod 3Z. This is checking elements of f. So f is irreducible since there exist no h over k inside f, where h and k are polynomials in y with coefficients in Z mod 3Z, such that h over k cubed minus y over 1 equals 0. Now, the easiest way to see this is to note that this would mean that h cubed is equal to y times k cubed. And you'll notice that the degree of the left-hand side has to be a multiple of 3, and the degree of the right-hand side has to be one more than a multiple of 3. So this can't happen. So that means that f is an irreducible element with repeated roots, which, if we didn't know already, means that the field f is not perfect. So in order to find a field extension, or the splitting field of f, let's think about how f could actually factor inside a splitting field. First of all, we know that all of its roots have to have the same multiplicity. We also know that that multiplicity has to be at least 2, because we've already proven that f has a repeated root. So f has at least one root of multiplicity 2 or more, and all of its roots have to have the same multiplicity. but f only has degree 3. And so it wouldn't be possible for it to have two distinct roots. If it had two distinct roots, then each of them would have multiplicity at least 2, which means that the polynomial f itself would have to have multiplicity at least, or have degree, rather, at least 4, which can't happen. So that means that the polynomial f has to factor as the cube of something. It has to have just a single root repeated 3 times. So that means that if we can find an extension field containing just one of the, just some root of f, then f will actually split in that extension field. So let's let E be the field f adjoin z mod z cubed minus y over 1. So this is our standard construction. This gives us a field in which the irreducible polynomial f has a root. So remember, f was x cubed minus y over 1. Here we're just moving to a new field with a new variable z that where the quotient is the ideal generated by what we get by replacing the variable in f with the new variable z. So now we have that z is a root of f in E adjoin x, or f bar I should say, by Theorem 161. Now notice that in E we have that z cubed minus y is equal to 0. So that means that z cubed equals y, or I should say z cubed bar minus y bar equals 0. So that means that z bar cubed equals y bar. So that means that in E adjoin x, we have that f, which is x cubed minus y, that's going to be equal to x cubed minus z, f bar is x cubed minus y bar. That means that it's going to, f bar is equal to x cubed minus z bar cubed, which is x minus z bar cubed, because everything is characteristic 3 here, so we can move the power 3 outside. So this means that z bar inside E is a root of f bar of multiplicity 3. So in this field E is a splitting field for f, and that's what it looks like when you're working over an imperfect field. It's possible to have irreducible polynomials with repeated roots.